Got anything? Concern? Nothing? Alright. Did you all download Mathematica?
Yes.
I got a couple nods, and then usually if you're staring straight ahead, that means no. You didn't even download it?
No, I have it.
Oh, you did? You said no. So you did download it?
A while ago.
Okay, okay. So everybody has it? It's okay, you can, who doesn't have it?
I think so, but I don't remember.
You think so, you don't remember?
Download it.
Okay, we're gonna use it towards the end. You don't have to like freak out. The reason I wanna know if you don't have it is I'm gonna pair you up with somebody who does have it. All right, but anyway, so two things I wanna do today is I wanna talk about like the SIR model a little bit more in depth, what we can actually compute quantitatively, and then what I wanna do with Mathematica is actually use the SIR model just to try to fit it to some data. Your book does this, and what I've done on my website is I've posted a Mathematica file, which has sample code for analyzing and fitting the data. So when we get there, we can add that. And then time permitting, we'll look at maybe SIS model, but we'll see. Okay, so I want to recall what we did last time. So we had this model. S dot was minus beta Si. Alpha I dot was beta Si minus alpha I, and R dot is alpha I. Is this visible? Okay. Is it visible on camera?
Yeah.
Okay, good. All right, so this is the model. And if I see a model like this, what's it telling me? What is this term modeling? What's that mean? Well, yeah, but the whole thing was this whole term modeling. It's not like an infection rate. Infection rate is the term. So this is just the infection process. But it's really saying, if I rearrange this, this is equal to minus beta I times S. The reason I did that is this term, like the left-hand side is saying the rate of change of the S population is proportional to the current susceptible population, where that proportionality depends on the number of infected. And that's just basically how fast people are getting infected. Okay? All right, so that's one term. What is this? The alpha I.
The flow from infected to recovered.
Good, good. So this is the actual you recovering, or basically probably better way to say it is, you may not recover, is you're just no longer infectious. Because you could actually still be sick and be infected, right? So this is movement of not being infectious anymore. Okay? All right, so that's the most basic model. And it's kind of the backbone of a lot of models. I mean, if you're really modeling a disease, this is the basic states you can be in. Okay, so then we asked a bunch of questions like, what do we actually want to know about this model? And so some of the big ones were, what is maximum number of infected? I'm just going to die. So what is the maximum number of infected, and how many people are infected? Those are big things we would just want to know at the onset of a disease. Okay. There are some other ones too, like just how much is this going to cost? What do we do in response? Those ones we have to do additional modeling. So from this model, this is all we want to be able to determine. Yeah?
The one you wrote in blue, do you mean at a given time t, or like at the end? Like
At the end, yeah. So this is, let's say throughout the pandemic. Because, so the question about how many people are infected, that would be like actually finding I as a function of t that satisfies these equations. That's challenging to do. We'd actually have to solve the differential equations. We want to get around that somehow. Okay? So there's a couple properties first that I want to figure out. So first of all, if you've had a course in differential equations, if you haven't, it's fine. I'm just going to write a property. Solutions, let me put down one more thing. So we also have to have a set of initial conditions. So this is the state of the disease at time 0. Right? So we have an initial susceptible population, an initial infected population, initial recovered. Generally, I mean, you can always start your time wherever you want to, but generally at time 0 there are nobody that's recovered yet. So generically I'm going to assume this thing is 0. Okay? There's another important property of this set of equations that n equals I plus, S goes first, S plus I plus R is constant in time. So that was baked into the equations. All right, so this is the basic model. There's one property of differential equations that's going to be really important. Solutions to ODEs exist and are unique. I'm being a little bit glib about the statement. Does anybody know what the true statement is?
Is that like the existence unique theorem?
This is the existence uniqueness theorem, and I cut out something. I basically just said solutions to ODEs exist and are unique. What I wrote is not 100% correct.
There's like a small portion.
A little bit more that you're on the right track, but it's like,
Something to do with partial derivatives. Unless I'm thinking of something else.
yes.
I don't remember what that said.
You can take involved partials, but it's something a little bit slightly different. Who's had 2P1 recently, or math modeling last year? What? After you look at grades, you did too.
Yeah, so she.
Okay, so this is a subtle thing, but these are functions on the right-hand side. So f dot is a function of s and I, right? The true statement of existence and uniqueness says the right-hand side has to be, starts with an L.
Lipschitz continuous?
Yes, the right-hand side has to be Lipschitz continuous. This is a smooth function, so who cares even what Lipschitz continuous means? It's definitely continuous. So in other words, this solutions to ODEs exist and unique for like essentially anything you can write down. It's a very powerful theorem. This is not true for things like partial differential equations or harder equations. But it says, the upshot is, if I have a solution, it is the only solution. And I'm guaranteed that there always is a solution. Okay? This is something that's going to be it's very subtle, but at the same time very powerful. Because it allows us indirectly to determine a lot of qualitative information about our solutions. Okay? So the first one I'm going to show is this theorem that's going to be a property of the solutions. So I'm going to write it this way. So if S of t solves, let's call this whole system star, then limit as t goes to infinity of S of t exists, and let's call it S infinity. Is greater than 0. Let's actually make it greater than equal to. All right. So I kind of discussed a little bit about this proof before. And I'm going to sketch this more than provide like a super rigorous proof, because I just more want the intuition behind it. Okay. So where should I start in showing this piece? Yeah, right.
Do you want to apply the monotone conversion?
Yeah, good. This is similar to what we did last time. How do I apply the monotone convergence theorem?
Because that number, the susceptible population, because you don't have that backflow, it always continues going down.
Okay, good.
Below 0.
All right, so the first observation is we know S dot is less than 0. Okay. How do I know that's true?
The susceptible population can only be going down.
Well, that's assuming what you want to prove, right? So S dot less than 0, but how do I know that's true?
Negative.
Well, what's negative? That's not. How do you know it's negative? I just showed you that.
Well, negative, positive, and susceptible and effective actually positive.
Okay, this is actually being a little tricky. How do I know S and I are positive?
The population.
Yeah, but that's an assumption, right? Like, that's something, you want that to actually be a mathematical consequence. Like, yes, that should be true if my model makes sense, right? But I actually want to verify that my model makes sense. Maybe I made something busted, and then when I actually solve the equations, the populations go negative. That would be super bad, right? So the first thing I actually need to do is prove something a little bit more subtle. I need to first prove, oh, sorry to do that. That's the worst thing a professor can do, is write something and then erase it. Sorry about that. That's from Zoom land. Okay, so anyway, probably gonna do that a lot. But so the first thing I actually want to show is for all t, S, I, and R are greater than or equal to 0. All right. This is a tricky, strange thing, but I'm going to do it. Let's just show it for S and I. So first thing I want to do is show if S naught and I naught are greater than 0, then S and I are greater than 0. The way I'm going to do this is there are actually solutions to these equations that I can find. Explicit solutions. And these equations would be, so like, if S dot is 0, what does that tell me about S?
Constant.
True, it's 0. But when your derivative is 0, what does that mean?
Constant.
Good, it's constant, right? So there are special solutions where you can look if it's a constant. So what I mean is, then that's my error. So I'm going to say note, S star of t equals I star of t equal to 0. These are solutions. Okay? How would I check that they're solutions? Yeah, Aiden, good. Plug it in, right? So if I plug in S and I equal to 0, that satisfies the equation because I have 0 on the right-hand side and 0 on the left-hand side. So these are solutions. Okay? So if I graph them, so I'm going to put down the S and the I. So these are the solutions that just stay at 0 for all time. Okay? All right. So now, if I go back to my initial conditions, if I say S naught and I naught are greater than 0, so that means, say, at time 0, I start here at some S naught. Okay? And let's say there exists some point in t, I'll call that t bar, where S of t is negative. How can this be true?
You have to find some place where S crosses over the x-axis.
Good, okay. So let me write this formally. So, whoops. Should be a note. Now, these are solutions, and I'm going to assume for contradiction, assume there exists some t star or t bar such that S of t bar is less than 0. Okay? So I know there's going to be a point where this had to cross 0. Let's call that t star. And here, S of t star is going to be 0. What's that theorem called? Starts with an I.
Intermediate value.
Yeah, intermediate value theorem, right? And it's, I love those theorems from Comp 1 because their names make sense. If there's an intermediate value that crosses 0, right? Okay, so there exists some t star such that this, or t bar, such that this thing is less than 0. I'm going to just abbreviate this and say by intermediate value theorem, there exists t star such that S of t star equals 0. Now, why is this a contradiction? Let me draw it. So who knows what it does? We know the derivative is always negative at least, so maybe it does something like this. Yeah?
Yeah, crossing solutions.
Why is that bad? Why not? What's that matter?
it existence uniqueness?
Yeah, so why?
That's not unique.
Yeah, why is it not unique?
Because at that time, you have two solutions.
Okay, it's if at this time, if I go to this point, right? There are two different solutions. There's the green one that goes down, and then there's the blue or the green one that goes to the right. Both of those are solutions given an initial condition that starts at this time. That is a violation of existence and uniqueness. This is a fundamental property of solutions or ordinary differential equations that they cannot cross. Okay? So that's the contradiction. Okay? So there exists such that this is 0. This is a contradiction. Which implies S is greater than 0 to do it. Okay? So the S is always positive. Yeah?
Go back over why the crossing based on that.
Yeah, so the way I wrote down the differential equations here, I started with like some S of 0 initial conditions, right? I could have said, okay, start at this point. So this would be like saying, let's start with some initial conditions. S of t star equals 0, right? And by existence uniqueness, if I give you some initial condition, you should only get one solution. But there are two solutions. There's the one that stays constant, and then there's the one that I'm saying should go negative. And that just can't happen. So the contradiction was assuming that this thing went negative.
Okay, that makes sense.
Good. Other questions? Okay. Okay. So this is a contradiction. So S is greater than 0. Why did we do this?
So it's more rigorous.
No, I could. No. Actually, I could make this even more rigorous. Yeah, so originally we wanted to use the monotone convergence theorem, right? So we know we wanted to say S dot is always negative, right? But to do that, I need to say S and I are both positive. So that guarantees this, okay? So what we now know is S dot is negative, okay? And it's bounded below. So this tells me limit as t goes to infinity of S of t, which we call S infinity, is greater than or equal to 0. This okay? This is a typical argument in ODEs where, yeah, we can't solve the thing, but we can use properties of the derivatives to deduce things from the equations. Okay? All right. So that helps with S of t. So this gives me this quantity. Okay, great. What about R of t? What can we say about that? What's the sign of its derivative? So it's positive, right? So R dot is positive. So it's definitely an increasing function, right? What else?
We have a bound on it.
What's its bound?
It has to do with the fact that we bounded it with n equals s plus I plus r.
Okay, good. So I'm just going to write this here, that we also know that well, we know R dot is positive and R is less than or equal to n. infections, okay? So what does that tell me about its limit?
It exists by the function.
Okay, good. So there does exist a limit. The limit is t goes to infinity of r of t exists, and we're going to call that some r infinity, which is going to be less than or equal to n. Okay. So big picture, why am I doing this? What does this help me figure out about the solutions to these equations? Well, let me draw a graph, and we'll use this information to piece together what the graph should actually look like. Okay. So, so let's say my S naught is here. And I want to just plot what the solution should look like as a function of time. What should it do?
Decrease.
Good, decrease. We know it's got to be going down. And then what?
Flatten out.
It's got to flatten out, right? It's decreasing down below by 0. So the S of t has to look something like this. Right. What does the R of t have to look like? Renata?
It has to be positive and bounded above by the total population.
Right, and it doesn't have to reach the total population, it just has to start increasing and then flatten out. So this is what the R of t looks like. Okay? All right. What do you think the infected should look like? So I'm going to write down the equations. So again, S dot is minus beta IS. I dot is beta IS minus alpha I. And R dot is minus plus alpha I, right? So what about the infected? What should it do at time 0?
0?
Yeah, it can be run well at 0. This is going to be the worst disease ever.
Oh, no.
So, but close to 0, right? We don't want it should be something very close to being at the bottom. So maybe I'll put it like right here. Okay. Then what? It's an epidemic. What happens to the number of infections? They definitely go up, right? Then what happens to them? What?
Decreases.
They better. Yeah, they have to decrease, right? If you have a recovery. So this is what we expect this curve to look like. Something like this. All right. How do I prove something like this? What do I need to know about the graph? Think about the properties we put in
Their
there.
sum is a constant.
Oh, we already know the whole sum is a constant, right? So we know S plus I plus R is always a constant. Let me give you a hint. There's a bunch of properties I actually put in this implicitly. One is asymptotes to 0. Okay, that's one of them. One is I prime at 0 is greater than 0. That doesn't have to be true. It could have actually been decreasing at time t equals 0. It could have been a really non-infectious disease. And then everything would just plummet. Right? So how would I prove this statement first?
Given what assumption? Given the other two, the S and the I as we have them?
Well, do we have to use the S-naughts?
Didn't you just say that it might not be
Right?
greater than 0?
Uh-huh.
So what are so what information are we using to prove? I'm
Well-
confused about the question. Sorry.
No, I'm just being mean. I'm a
Okay.
very contrarian person. So, if I actually want to figure out a derivative, what's the only thing I can use? It is on the board. Well, there's this derivative. Where else is there an I dot? There, right? So this is the only thing that's relating I dots, right? So how should I figure out what I dot of 0 is? Don't overthink it.
Take the derivative.
Well, I heard a bunch of things. Robert?
Can we use S dot and I dot as 0?
Well, we don't even need the S dot. We just need the I dot.
Or I meant R dot.
We don't need that one either, just the I dot.
Just take the derivative of the right-hand side of.
Way too hard. Think like a cap one.
Plug in 0 for I.
Yeah, why don't you plug in 0? So literally I'm asking I dot of 0, right? This is I dot as a function of these things, right? So I dot of 0 is beta of I of 0 times S of 0 minus alpha I of 0. That's it. This is the condition. If this quantity is greater than 0, this implies epidemic. That's it. Nothing more than that. But let's say we're in a really, really large population. What is S0 approximately? What's that? Not that big. We don't want infinity. But think about like at the beginning of COVID, right? How many infected were there? A couple. That's great. How many susceptible were there?
Like the entire population.
Billions, right? So it's a wholly different scale. So the S naught originally was equal to, so I'm going to approximate this by beta times, I'm going to keep this as I naught times S naught, which is approximately N minus, oops, can't do that. So this is beta N minus alpha. Has to be greater than 0. Is this okay? So what conditions on the constants guarantee that this grows in time? Kat, you blinked funny at it. That's just you blinking?
I mean, maybe. I was just thinking, like, we said that, did we assume that the initial condition for that was positive?
Better be, yeah. So I naught, S naught, R naught are always going to be positive or equal to 0. But we're definitely going to assume there's some positive infection. So if I have a product of two numbers, how are they ever positive?
Well, in this case, beta would have to be greater than alpha, so that the inside.
What about N? You forgot that.
But n is positive. So.
Yeah, but it's not so it's just an algebra problem where you say, look, this thing I know is positive. I want this whole thing to be positive, right? So this implies beta N minus alpha has to be greater than 0, right? So this, I'm going to rearrange this as beta times N has to be greater than alpha. Usually in epidemiology, this is written in this form. So that is the condition for an epidemic. It does take into account the population size, the number, how like the force of infection, and the recovery time. Is this okay? So this quantity comes up enough that it's given a name. So this is what's known as R naught, or the basic reproduction number. And it does tell you whether or not an epidemic will occur. You got to be careful with that type of language in this model. Okay? All right. Any questions about this condition? So this was the first part of what we wanted to prove, is that I prime of 0 is greater than 0. So that will only occur if this condition is satisfied. Okay? The other condition was about this thing flattening out to 0. How do I prove something like that? This one's tricky. So I'm going to walk you through the proof of this one. I'm going to do it pretty quick because it's not like one of those proofs that's like super important. But it's just like a nice math trick. And it's a good review of these actually. So let's see. How do I want to do this? I'll do it this way. So if I look at the equation, S dot is minus beta IS. Okay. And what I'm really asking for is information about I as time goes to infinity. And what I'm going to do is integrate both sides of this equation from 0 to infinity of S dot dt is equal to minus beta, the integral from 0 to infinity of I of t times S of t dt. Okay? Any guess on why I'm doing this? Maybe I'll give you a hint. What's the left-hand side become? What's that integral?
That's just S.
Not just S. Careful.
Plus C.
Plus C. What type of integral is it? Definite. It's probably improper too, but it's also definite. So how do you evaluate, what's the formula for your calculus say? Heard from somebody.
S infinity minus S0.
Good, good, good. So this is S infinity minus S0, right? So this is just S infinity minus S naught. Okay? And then this is minus beta times the integral from 0 to infinity of I of t times S of t dt. Okay? This is a bit of a trick because, I mean, these things are tough to think of when you're first facing these as students, but I'm trying to relate to information I know about, which is the S infinity and the S naught. That's information I can control. I'm somehow trying to introduce that to stuff I don't know what it is. Okay? I'm going to simplify this. So this implies S naught minus S infinity is equal to beta times the integral from 0 to infinity of I of t times S of t dt. Okay? Then I'm going to do something tricky, which is to say this is greater than or equal to beta times S infinity times the integral from 0 to infinity of I of t dt. So what did I do there?
Since S always goes down, S infinity has to be less than S.
Good, good, excellent. So I know this S of t is a monotonically decreasing function, right? S infinity was its asymptote. So inside the integral, I can replace that with an S infinity as long as I say this is greater than. So this is a true statement. And then what I did is this is just a constant, so I pulled it out of the integral. That's okay? Okay, so this tells me whatever this number is has to be related to this integral. So what does that tell me about I of t? What does an integral measure? What's that, Steve?
Area.
Good. It's the area under the curve, right? So this quantity is the area under the curve of I of t, going all the way from 0 to infinity, right? I is a positive function. It has to be a finite number because the left-hand side is finite. How is that possible?
S infinity is fine.
No, S infinity is just a number. So we know S infinity is bound between n and 0, right? Let me draw it. So I have some function I of t, right? And I know it's got to be 0, right? And what we want to show is it does something like that, right? So that means we need to eliminate it doing something maybe like that. We don't want it to go off to infinity. What's the area under the curve for the red curve?
From 0 to infinity?
Yeah.
It's divergent.
Good. Yeah, it's divergent. It's infinite, right? And in fact, if I of t goes to infinity, what would its area be?
If the function value I of t hits
Mhm.
infinity, as t approaches infinity,
Yeah.
it'll be divergent.
Yeah, it's that easy. So in other words, if the limit as t goes to infinity of I of t is infinity, it's definitely infinite, right? Okay. So for this thing to occur, I'm going to write down some observations. So therefore, this integral is finite. Okay? I'm going to say consequently, the limit as t goes to infinity of I of t cannot be infinity. Okay? Can it be a constant? Aiden? Why not?
Like you integrate like a constant for an infinite amount of time, you have like an infinite long rectangle.
That's right. Yeah, so what would happen is if I tried to say, let's just say it's a constant, then this thing would be flat, but I'd have an infinite area here. Right? Can it do wiggles, but not go to 0? Why not, Melinda?
Because then it would also be infinite.
Yeah, it still would be an infinite area, right? What's the only way it can have a finite area?
Approach is 0.
Yeah, so it's a little bit more complicated than that, but I'm going to say this implies limit, or sorry, this implies this. Technically, you need another condition that your function is uniformly continuous to say this, but we're working with ODEs. The functions are very nice. You could technically have a function that makes like a big spike, comes down, that makes another spike, but the spike is more narrow. So just because areas have to go to 0 doesn't mean your function has to go to 0, but it does if you're uniformly continuous. Okay? But the intuition behind this is more important. This argument is very standard, where you just say, I know these quantities, I have some integral that it's equal to, So the limit of what's inside the integral has to be 0. Okay? So this is the takeaway from this calculation. Okay? So this condition is always true. So I'm going to write down the properties that we know for I of t. So I'm going to say if R naught is greater than 1, this implies I dot of 0 greater than 0. And we know the limit as t goes to infinity of I of t has to equal 0. Okay? So in other words, the graph has to look like this blue curve. It's got to go up and then come down. How do we know it doesn't go up? How do we know it doesn't go up, down, up again? How do we show that? We can, yeah. We'll come back to that in a bit. There's actually even, I'll answer that question a little bit later when we do SIS stuff. That's a harder question. But one of the questions that we started this class with was trying to answer what is the maximum number of infections, right? And we wanted to know what was the maximum, how many total people were infected during the pandemic, right? So how do I calculate the maximum number of infections? What's that, Grace? You went like this?
Yeah, I did.
Why?
I don't want to talk in class.
I know you don't, but that's it. So I'm going to call you out that this, you meant this, right?
Yeah.
The maximum, right? So how do I find the maximum of a curve?
The derivative equals to 0.
Good. So you got to be careful with what derivative, but what we care about is where I dot of t equals 0. Okay? So the max occurs when s dot of t equals, or I dot of t. Okay? And how do I find that? Good, good, you're getting it. Yeah. So all I have to do is plug it in, right? So let me write this condition here. All right. So based off of those equations, I dot equals 0 implies that you have beta times, I'm going to call this like I max, times S minus alpha I max has to equal 0. Okay? So if I calculate this, I'm going to get I max is equal to, wait, what did I screw up? No, that's not what I want. Sorry about that. So when this equals 0, it's really a statement about the S, right? So the S, I max occurs when S equals alpha over beta. Okay, let's call that S max, too. That's kind of weird, because it's not where its max is, but I'm just going to call it that. Okay. Why is this helpful to proving that the I can only go up, then come back down, and never come back up again? Let's write down what we know about. So on this graph, this green curve, that's where my S max is, right? So really it should be on the horizontal. This is where S max is. And this is where the I max is. Okay?
Because S is monotonic?
Good, yeah. If it ever occurred again, right, the S would have to be at the same height, but that just can't happen. So once there's a maximum, it just comes down and never comes back. So this is something that's actually a problem with the SIR model. It can only have one bump. It can't have multiple waves. Okay, so this is definitely a bug, not a feature. Okay. All right, so that's one thing. The bad thing about this doesn't really help us determine what is the actual maximum number of infected. All this tells us is when we are at the maximum number of infected, what we know is that my susceptibles have to be at this ratio. Okay? So that's not the most useful thing. But it does give us a hint. If I can relate the infecteds to the number of susceptibles, independent of time, I can determine this. Okay. So this is another trick of ODEs, is I'm going to look at these equations, put into words what I just said. I want to find a relationship between the S's and the I's independent of time. So I'm going to write this as S dot over I dot. So that's the same thing as dS dt divided by di dt. Right? All I did was just write what those things are. Right? Well, trick. Why is this true?
We're dividing by a fraction.
Is di dt a fraction?
I mean, not technically.
Well, when so first interrupter, everybody's probably quiet because it's a trap. They're not fractions, and I'm going to be a little bit mean about, not to you personally, but mean about this is not, they don't actually cancel. So what you're really doing from this to here is, this is chain rule. So I'm going to rewrite this. ds dt is the same thing as ds di times di dt divided by di dt. And then these cancel, and you get ds di. Okay? Why am I being a jerk about that? Why does this matter? Where does this go wrong? What happens with second derivatives? Okay, so this relationship here does not, if I wrote this as d squared s dt squared divided by something squared, they definitely don't cancel as fractions. It's really easy to screw that up. Also, if you do higher math where you're working on curved surfaces or something, these are not fractions, they're derivatives. And you have to use the chain rule correctly to cancel these things. And it definitely doesn't work if they're partial derivatives. So I'm always a little bit careful, even when I do it, is think, oh yeah, this is not actually dividing by fractions. This is just chain rule. Okay? It's a shortcut, but be careful with some of those shortcuts. Okay? All right, so anyway, ds di is s dot divided by I dot. So I'm going to write out what that means. So this is negative beta is divided by beta is minus alpha I. Okay? Why is this helpful? well, what can I do to this fraction?
I's cancel.
Yeah, definitely the i's can drop, right? So I can rewrite this first as minus beta s divided by beta s minus alpha, right? Okay. How's that? Why is that helpful? Melindy?
Well, aren't we looking for when beta s is equal to alpha?
We could.
Or not equal, but.
Okay, so yeah, so this, actually you can see this, right? So this is actually a measurement, this is a little bit weird, because these equations were functions of time. So this is like an s dot, these are both two functions of time divided by each other. But then I got functions of just s's. What does this quantity measure physically? In Calc 1. So when you guys learn about derivatives, what do they measure?
The rate at which s is changing is a function of I.
Good. And what's that geometrically?
The slope of the
Yeah,
tangent line.
slope,
graph
right?
s to I.
So this would be the slope of, if I graph this thing. So Melindy, back to your question about like when s is equal to alpha over beta, why I'm asking that is when s equals alpha beta, this thing is infinity. Why does that make sense? Let me flip this equation a little bit. So this implies the IDS is equal to beta s minus alpha over negative beta s. So now what happens when s equals alpha over beta? What is the IDS? Zero. So why is that useful? So what happens when you have a zero derivative? Grace, you're putting your head down. What happens when your derivative is zero?
A local maximum.
Yeah, that's a maximum, right? So that's actually what was happening. I had them flipped, so that was like the flip of the variables, but then I put it in this form, that is where the maximum is going to occur. But it still doesn't tell me what I is. Like this is a relationship between a derivative and a function. How do I get rid of the derivative? What's that, Matt?
Integrate?
Yeah, why can't I just integrate? Yeah, it's separable. You can think of it as a differential equation that's separable if you've seen that. Or this is literally saying take the derivative of a function with respect to s. Here's another function with respect to s. Figure out what that function is, right? So I could just undo this thing. I'm going to rewrite this as, I'm going to write this a little bit fancier. So this is the integral from 0 to I of di is equal to, oops, I naught. This is s naught to s of, I'm going to simplify this. So, well, that's a negative 1. And then this is plus alpha over beta s ds. Okay? I definitely avoid indefinite integrals. You should get used to definite integrals. So I'm just integrating this from where I naught, when I equals I naught, s equals s naught. That's it. That's all I'm doing. Okay, so it's like tagging the same place that the integrals have to start at. Okay. So I can just do this integral, and I get I minus I naught is equal to this integral, So that's going to be S naught minus S, and then plus log of, shoot, let me not mess that up too bad. So this is plus alpha over beta log of S over S naught. So it's okay, I skipped a bunch of steps. Properties and logs too. So you should have a difference of logs, I just put them together. Okay? Okay, so this formula is the connection. If you give me a susceptible, I can figure out exactly how many infected there are. Okay? This is a fundamental formula connecting these two quantities. Okay. Great. How can I use this formula to answer the question of what is the maximum number of infected? Yeah?
Can we just add I naught to both sides?
Okay, good. So let's convert this to being in I equals I naught plus S naught minus S plus alpha over beta log of S over S naught. Okay, good. Now what? Another?
Well, we know that I max occurs when S max equals alpha over beta, so can we plug S max as S?
Good, okay. We know, whatever, oh, it's right there. So we know this is the S value at which the maximum occurs, right? So I can just plug that in, and that's got to be my I max. So I max is equal to I naught plus S naught minus alpha over beta plus alpha over beta times log of alpha over beta S naught. There you go. There's an explicit formula. If you know the initial number of people infected, the initial number of susceptibles, and you know the infection rate and the recovery rate, you can figure out immediately from this model how many people are going to be infected at the peak of the epidemic. Okay? So this is not the way epidemiologists write this equation, though. How can I approximate this? At the beginning of the epidemic, how many infected individuals are there, roughly?
Very few.
Very few, so this is going to be a super small quantity, so roughly 0. What's S naught going to be?
N.
Yeah, roughly N, right? So what I should get is the following. So I'm going to get I max is going to be approximately my I naught 0, so my S naught is N minus alpha over beta times the log of alpha beta N. That's okay?
Did you drop an alpha over beta term?
Almost certainly. Where did I drop? Yeah, right here, and then minus alpha over beta plus alpha over beta. Good. Okay. Any other mistakes? Okay. Now, I'm going to factor this n out and say this is n times 1. How do I want to do this? So that's fine. Minus alpha over beta n times 1 minus log of alpha over beta n. Okay. How can I put this in terms of R naughts?
For all the alpha over beta and it's 1 over R naught?
Good, yeah. I always screw that up and say it's R naught, but it's 1 over R naught. So this is equal to n times 1 minus 1 over R naught times 1 minus log of 1 over R naught. Good. Okay. And I'm going to do something probably dumb, but what we should do. What I do there?
Oh, you move D on -1 inside.
Yeah, or the other way, it's a 1 over R naught, which is R naught to -1, and pulls it out. Either way, it's properties of logs, right? Okay, so this is the formula. So this is my total population, right? This number here is going to be multiplied times this. Okay, that's obvious. So what is this quantity here? Like if I have the total population, I multiply it by a number, what does that give me?
A fraction.
Yeah, this is just the fraction of the total population that will be infected at the peak, right? So that's what this whole quantity is. This thing is the fraction of whole population infected at the peak. Okay? Good. So that really does answer one of the questions. This model, even though we couldn't solve anything with it, like we can't solve these equations, we're able to deduce just from like proving some things, at least some quantitative information. These are just physical things you can measure. And that's it. So this is one of the reasons if you hear this in the news or like, epidemiologists are obsessed with finding R naught because it immediately tells you these quantities, like how many we expect to actually be infected. Okay. All right. The other quantity I want to compute is the total number of infected during the entire pandemic. So what's that number? Hello?
Would it be close to N or no?
No, it doesn't have to be. It could be a really crappy epidemic. Yeah?
The integral of RT.
Not the integral, actually. We just need to find R infinity. Right? So that's what we need to find is R infinity. And we're going to use some tricks to get to it. I'm going to start erasing stuff. Just don't let me erase this. Okay? Okay. So this equation tells me immediately, if you give me a number of susceptibles, I get the number of infecteds, right? So how can I use this to get the number of recovered?
Could you repeat that?
Yeah, so like, this equation does relate everything. If you give me an S, I can figure out the number of infected, right? But what we really care about is we want to compute this quantity, which is R infinity. That's what I really want, right? So I could try to find other differential equations for RT, but it's challenging. How could I use the S and I's to determine this quantity?
Do we have S infinity and I infinity?
What do you think I infinity is? Yeah, good. That's one thing we proved, actually, right? So I know, boy, how does that help?
N minus.
Good, good, good. Okay, so what I know is this quantity, R infinity, is equal to the limit as t goes to infinity. Just wrote down the exact same thing above. Is equal to the limit as t goes to infinity of n minus s of t minus I of t. Right? So I can plug this in, right? So the limit as t goes to infinity of n is, well, that's just n. This is my s infinity, and this thing is 0. Okay? So what I actually need to calculate is s infinity. How do I calculate s infinity? Well, what's the only equation we have, really? Well, that's a terrible question. We have tons of equations. What's the one equation that's boxed?
Over there.
Yeah, so this is the one that tells us everything, right? What would happen if I plugged in s infinity into this? Yeah?
Would I need to be infinity? Would we need an I infinity?
Yeah, what's I infinity?
0.
Good. This is telling us, give us any s, we also figure out the I, right? But we know what the I is at time equals infinity. So from this equation, there's a reason I didn't want to erase it. I know that negative I naught is equal to s naught minus s infinity plus alpha over beta log of s infinity over s naught. Is this okay? All right. How can I approximate this thing to make our life easier? Good. The I naughts are basically 0, right? What are the s naughts? N, right? So what I can say is then I get 0 is approximately n minus s infinity plus alpha over beta times log of s infinity over s naught. That's okay? Huh. Probably means I have a typo in my notes then, because I have an actual formula for s infinity.
Should we have the n in the bottom of the log?
Let's see, the n in the bottom of the, yes, thank you. There should be an n here. Okay. Let's see, what did I do? I don't know, I just made a mistake. But, so this is the relationship between the s infinity and the quantity. So I can solve this equation. How do you solve it? It's a trick question. Why is it a trick question?
Use a computer.
Yeah, that's basically what you have to do. Unfortunately, at this point, this is a transcendental equation. You have a log here and a linear term here. Somehow this is missing in my notes, and I just solved for s infinity. I remember writing, I was like, man, I don't remember ever doing that before. I was just went with it. And then it's probably the dumbest thing I've done in a long time. Okay, so this you can only solve numerically. But once you have it, you can plug it in here to get the total number that we infected during the pandemic. Okay. So I overestimate how long this would take. This is what we're going to use Tuesday to fit data. Have Mathematica installed, ready to go. Matt, find it on your computer. You got to find it too on your computer, right?
Yeah.
Okay. All right. Any questions? Concerns? Worries?
With the fraction of the p, would that be that with the one minus, so if we take that out of the shift, we can get at the fraction of not affected that as well. Right?
Yes, very good. So the fraction that's not infected, well, actually, no. So this was the maximum number of infected, right?
I mean,
There will be people that are recovered at that point. So we can't just do 1 minus this. Because there will be a susceptible population, and an infected, and a recovered. And so we can't actually get to the number that are still susceptible.
Is this the fraction that are infected?
Is this whole quantity? Yes, the whole thing, sorry. All right. You know what I missed is seeing all your guys' cuts.